Now, one thing, I received the response from the Enviro and Geo about the preferable day for the tutorial, which will be next Tuesday, except for some times like the class time, office hours, as well as the they have certain office hours. So if you please the AE, if this date is good for you guys, that will be perfect. So we will go for that. If no, then I will have to manage another day as well. So please, if you can respond to me, AE students, through your class reps, of course, uh, by tomorrow. So on Thursday, I will announce the tutorial. Okay. Okay. So let's start our lecture today, which is about nodal analysis or a nodal method. So this is basically a technique that can be used to analyze the circuits. And definitely there was a question now will be raised, which is the following. Now, what we know so far, we know KCL, we know KVL, and Ohm's law. And for your information, I can solve any circuit in the world using these three techniques: KCL, KVL, and Ohm's law. So the question is why we need to know other technique? Why we need to know nodal? If I can use this technique to analyze theoretically and practically, actually, any circuit, then why I have to learn extra technique? And to answer this question, I will demonstrate this with an example. So let's assume that I have this circuit, which is a typical, this is like a Wheatstone bridge circuit, actually, unbalanced because R 1 ohms and R prime is 2 ohms. So this is an unbalanced circuit. So it means there will be a current here, and VA doesn't equal to VB. Okay, so if this is, I have a circuit like this, and remember, this is not an open circuit, so this is different than the ones that we used in the strain gauges. Okay, and I want to find IAB. Then how to do that using the classical techniques that we know: KCL, KVL, and Ohm's law. So as you know, the first thing you need to do is in every single branch, you need to assign a current, and then you need to assign a polarity as per uh, the passive convention that we learned. So if you do that, then we will have a current I coming off the 13-volt battery. Then we have ICA, ICB, and use this CB between the points, IBD, IAD, and IAB, and I. So how many unknowns do we have here? We have 1, 2, 3, 4, 5, 6 unknowns. So if I have 6 unknowns, then I need to have 6 equations. And without the need to go to any details, okay, so these are the equations. So we apply KCL at C, KCL at A, KCL at B, and KCL at D. Okay, so we have different KCL currents. So for example, KCL at C, it says I is equal to ICA plus ICB, etc. And then we applied to KVL. We choose 2 loops. Okay, so we have this loop and we have the outer loop. So this will be like plus minus plus minus, because this is this as per the current direction, plus minus plus minus. So let's see just KVL to loop number 1, which is the red one. Then it says ICA times R, which is 1 ohms, plus, so going this plus minus plus minus, IAD times also 1, so IAD, continue the loop, minus 13 equal to 0. Of course, we have this loop, that loop. We have also this small loops. So I can choose any of these 2 loops, or I can choose 3 loops and 3 KCL. So I can have combination of this, and then I can find the unknowns. Now you can imagine how tedious is to solve this circuit. 6 unknowns. I have to solve these equations. So that will be like very time consuming. And if you do that, you will find IAB equal to -1. Please don't don't even try to solve it. There is no point, because I will never ever give you a question like this with all these unknowns. Okay, but here, just to demonstrate my point, that although KCL and KVL theoretically and practically can be used to solve any circuit, sometimes the circuit becomes very intense in terms of the math and becomes almost not practical to solve it with hand calculations. And imagine if I'm just adding a little bit of more complexity, then we will have too many equations to be solved by hand calculations. Then I have to use IPC to be able to solve this. So this is the main incentive, that okay, we need more efficient techniques. Okay, so this is not a very efficient, because the number of equations are large, and also it's not systematic. As I said, you could have a different number of KCLs, you could have different number of KVL. So even if I assign the same question to different students, we might end up having different equations. Maybe if all of them solve the equations correctly, you will get the right answer. However, you will have each one of the students will have different different equations. So this is not a systematic way. We need a technique that is, first, give me less number of equations so that it will be less demanding to solve them. Second, I want to have a systematic system so that I will come and ask, there is no any other equation. It is, the system is designed that I will have the exact number of equations. Every student will get exactly the same number of equations. So that is the incentive. So if I was given a circuit like this, and let me identify the nodes. So here we will have one node, and here this is another node, and this is a third node. So here, what if I managed to find this voltage? Let me call it V1, V2, and V3. So if I manage to know every nodal voltages, okay? Now, what if I want to find the voltage plus minus, I will call it V across 6 ohm. So if you want this voltage, actually, the voltage across the 6 ohm is nothing but V1. Okay, start acting weird. Okay, just a second, please. Sometimes the pen act weird, so I need to just no, this is something wrong here with the pen. Let me just try this and come back. Okay, so let me clean everything here. Sorry about that. Sometimes, you know, this technology is not very robust. Okay, so let me just take this out, take this, remove this completely. Let's start over. Okay, so here, as I said, this is your V1, this is V2 and V3. And if I want to find the voltage, I call it V across the 6 ohm. So your V across the 6 ohm is nothing but V1 minus V2. What if I want to find this current? I will call it I. So you across the 7 ohm. So your I across the 7 ohm is equal to this voltage V2 minus V3 divided by the 7 ohm. What if I want to find the power dissipated in the 2 ohm? What is this power? The power in the 2 ohm is equal to I square times R. Okay, so I square times R. I know I. What is I? I is nothing but V1 minus V3 over 2 square, and this is your current, and then I square R, you will get the power. So what I want to say here is the following, that your power calculations, your voltage and current calculations, anything of this can be done using nodal analysis, because in nodal analysis, it will give me V1, V2, and V3. So if I can find these nodal voltages, then I can find anything in the circuit. So the whole problem now becomes how to find these nodal voltages, and hence after that I will be able to find everything in this circuit. So what are the steps in the nodal analysis? Okay, so the nodal analysis has certain steps that we need to pay attention to. These steps are the following. First, select a node as a reference. So let me have this circuit. We have a voltage V, R1, R2, R3. So we select one of the nodes as a reference, and usually we select the node that is connected at the bottom. This is usually the node that we select, and usually it is given to you. So this is the node we could select it as a reference, and we assign the voltage here V equal to 0. So we know the voltage, and we assign its value, and everything else we calculate is with respect to that reference. Now, when we assign a voltage to one of the nodes, it means what? It means that we already know one of the nodal voltages, and this will reduce the needed number of equations. So select a reference, we assign a voltage equal to 0 to that reference. It's basically, in electrical terms, this is what we call the ground. So everything has a ground. Your home has a ground where you have a wire connected to the ground, digged inside in the ground few meters, and we assume that the potential or the voltage is 0, and everything in your house is with respect to this reference. Then we will assign to the other nodes the voltages. I will call this is V1, V2, etc. This is the same node, so this is, I don't need to assign. If there is a resistance here, R5, then or R4, so this is another node. Okay, so if we have an n number of nodes, we will assign up to n minus 1. Why n minus 1? Because we already assign a node to the reference. So we already, one of the nodes has been already covered. So this means that I will need an n minus 1 equations. So this is one of the clear advantages of the nodal analysis, that we already know the voltage at that specific node. Then we will apply KCL. And here I'd like to pause a second. In nodal analysis, and this is one of the other advantages of the nodal analysis, we only apply KCL. We don't apply KVL at all. We never apply KVL in nodal analysis. Okay, so we will apply KCL. However, the KCL, we will apply it in terms of the node voltages, not in terms of the currents. Meaning, if I have this node, this is a current entering here. Yeah, ground is the voltage is equal to 0, and a current like this, and a current like this. So this current is equal to this plus this. How I will represent this current? I will represent it as V1 minus V2 divided by R1. So this current that enter the nodes. This current that leaves the node, so this is equal to V2 minus 0 divided by R2. Plus the current that goes to the right is V2 minus V3 divided by whatever R3 or whatever the value is. Okay, so it's a KCL. However, we don't assign current I1 and I2, but we represent the currents in terms of the nodal voltages. So my unknowns here will be the nodal voltages, which if I solve and find those all nodal voltages, then anything in the circuit I can be calculated. As I have seen, current, voltage, power, anything you want in the circuit can be calculated once you know what is the value of every single nodal voltages. Solve them, and then we obtain the unknown voltages. So we will have three scenarios. Two of them will be covered today, and the last one will be covered on Thursday. Okay, so what are the scenarios? The first one will have circuits with only current sources. There is no voltage source. Okay, so we will apply what we said. One of the nodes as a ground. So this is given to us. So here it's your V is equal to 0. So this is your ground, V equal to 0. And then we'll have 1, 2, 3 nodes. Total we have 4. So we need to assign voltages to 3 of them because the fourth one we already know the voltages. So we have V1, V2, and V3. So how many unknowns we have? 3 unknowns. How many equations we need? 3 equations. So now we need to assume the current directions. What I do, except for the current sources that I cannot change its direction, all these are one ground. Whoever is asking about this, all of these are one. Remember, all of these is just one ground because there's no component between these points. So everything here is just one ground, and this ground has a voltage that has been assigned and known. Okay. Now, so we'll have V1, V2, and V3. Now, how to assign the current? It's up to you. You can assign them in a very random way. Entering, leaving, it's up to you, except for the current source you don't touch. For example, this current source is leaving V1, so we keep it leaving V1. We don't change its direction. And it's entering V3, we keep it entering V3. About the rest, so what I usually do, I assume always to be consistent, the currents are leaving. What if I assume all of them are entering? You'll get the same answer. What if I assume them some leaving, some entering? You will get the same answer. But this is my convention. That is, I use since I was in your age. So I will assume all the currents are leaving. And when I move to the other node, I reset these current as if they don't exist, and again I will reassign the current direction, assuming again all are leaving. So let's see here, KCL at node 1. So now we will represent the currents in terms of the nodal voltages. So the current that goes to the bottom, it is V1 minus 0 divided by R1 plus the current that goes to the right, V1 minus V2 divided by R2. The current that goes to the top, it is leaving, so plus IS equal to 0. IS is given to you. So the unknowns here is V1 and V2. Okay, now to make things clearer to you, maybe at the beginning I will do this. So let me just clean the current direction so that you will not be confused. Let me select my pen. Let me change the color. So at the beginning, let me do it slowly, and then later on, we will do it fast. So here again, I will assume the currents are leaving as well. So KCL at node 2. So this current to the left leaving, so it is V2 minus V1 divided by R2 plus the current that goes down, V2 minus 0 divided by R3. The current that goes to the right, V2 minus V3 divided by R4, and this is equal to 0. So now we have two equations and three unknowns, V1, V2, and V3. We still need one more equation. So let's again clean this so that as if I did not assign anything here. And let me have my pointer here, and let me change the color as well. Okay, so here the current leaving, and I don't touch this current. So KCL at node 3. So the current here leaves, so it goes from the V3 minus V2. Why V3 minus V2? Because this is the current direction I'm assuming. If I assume the current in the other way around, it will be V2 minus V3. The current goes from the higher potential to the lower potential. So it is V3 minus V2 divided by R4 plus V3 minus 0 divided by R5. And this current enters, so minus IS equal to 0. Okay, so with this, I'm done with the KCL with the 3 nodes, and I'm ready to solve them. But here I will not solve this question. This is just to give you an idea how to do that. Why do we subtract V2 minus V1 and V3 from V2? Why we do V2 from, I mean, I don't, Sarah, if you explain, if you want to elaborate more on your question. I don't get your question. Oh, okay. The nodes are okay. When I say 1, it means V1. When I say 2, it's V2. 3 is V3. So the labels goes with the voltage numbers. It's always the case. So the voltage numbers, V1 is your first node, V2 is your second node, and V3 is your third node. So it goes without even the need to write them. Okay, but okay. Okay, so let's move on. Can you please explain why? Okay, let me ask. I don't want to move on because this is the foundation of this, so I want to make sure that everyone understands everything. Can we please explain why we assume the current is leaving from each of them? Okay, let me do this experiment, William. Okay, okay. Let me go back to V1. Let me go to V1. Okay, let me assume different directions. Okay, I will do that only for node number 1. So let me assume the current here is entering here, I mean, enter the node here, also like this. This leaves, this enter. And let me write the equation and let me see how this is different than this equation. If we get the same equation, then it doesn't really matter. It's just your assumption. So let's see this one. This current leaves the node, so it is V1 minus 0 divided by R1. This current enter the nodes, so this will be equal or minus V2 minus V1 over R2. Why minus? Because now this is against or in the opposite direction of my convention. I'm assuming current leaving are positive, so current enter will be negative, or vice versa. It doesn't really matter. And this is leaves plus IS equal to 0. So this is the equation we have now, assuming the current going inside the node except if going outside the node. So this becomes V1 minus 0 over R1. Now I will take negative here as a common factor outside, so this becomes plus, and this becomes positive, and this becomes minus over R2 plus IS equal to 0. When you look to this equation, it's exactly the same as this equation. So it doesn't really matter the direction of the current as far as you are consistent. Current enter the node is positive, current leaves the nodes are negative, or vice versa. Current enter the node are negative, current leaves the node are positive. And you go with this, it doesn't really matter what are the directions of your currents. Any direction will be fine. And this is why I said, okay, I'm assuming everything is leaving. To be it's easier, because if I assume something enters, something leaves, what will happen here? As you can see here, this current leaves, it's positive. This current enters, has to be negative. But here it is much easier. And then you notice one thing, another advantage, when you assume all the currents are leaving, so you have every equation in KCL with voltage difference, start with V1, V1 minus, V1 minus. Here for 2, V2 minus, V2 minus, V2 minus. So this becomes more consistent and everything is positive. So you don't need to worry, is it entering, is it leaving? Which one is positive? Everything is positive, everything is leaving. So that becomes much easier, and the susceptibility to do a mistake will be very, very less. Okay, now let's go for the second case where we have a voltage source, not a current source. So the current source is okay. Now, again, we'll do the same thing. We will assign nodes. This becomes V equal to 0. This is our reference. Now, one thing you notice here, that what is V1? V1 is the voltage between this point and the ground. And between this point and the ground, there is only one element, which is the voltage source. So basically, you can see clearly here that actually V1 is equal to Vs. In another word, V1 is given to us. We know its value. So this will lead us to a very important thing in Nodal. Do not apply KCL at a node connected to a voltage source. Why? For two reasons. The first, I already know the voltage, so I don't need actually to apply KCL to this. Second, remember, what is nodal analysis? We apply KCL in terms of voltages, but we need to have a resistance between the two nodes to find the current. Between this node, there is no resistance. So I cannot represent the current as in terms of R. So what I have to do, I have to assume a current called I here. So what I'm doing here, I'm adding an equation with another unknown, which is I. So I don't need to do that. So this is why we don't apply KCL at a node connected to a voltage source. This is something very, very important that you need to pay attention to. So now here, the number of equations has been reduced to 2 actually. We have KCL at V2. So KCL at V2. Again, we'll assume the currents are leaving. So it is V2 minus V1, which is Vs, which is given to us, divided by R2, plus the current goes down. It is V2 minus 0 divided by R4, plus V2 minus V3 divided by R3. And that's it. We have 1, 2, 3 branches. We have 1, 2, 3 items. There should be matching between the number of branches and the number of items in the equation. Sometimes we might forget. So make this exercise every time to make sure that they are matching, at least at the beginning, because still you are not very familiar with the technique. Until you master it, then you don't need to go and check every single point like that. So this is equal to 0. Then I will come here, apply KCL at V3. Again, I will assume the currents are leaving. So the current to the left is basically V3 minus V2 divided by R3, plus the current that goes down, V3 minus 0 divided by R5, plus sometimes, especially those type of currents, students overlook. They look just around here and they overlook there is a current that goes all the way from V3 to Vs. So this is plus V3 minus Vs divided by R1 equal to 0. So two equations, two unknown, because Vs, we already know it. And we will solve this. So here I put here clearly, do not apply KCL at a node that has a voltage source, unless you are asked to find the current at this node, and I will come to this later on. Okay, so here let's have, this is an exam question. This is a typical exam question. Okay, so here find the node voltages. We need to find V1 and V2. Now we have to see how many nodes we have. 1, 2, 3, but I only assign V1 and V2. Why? Because this node, which is node number 3, I know the voltage. The voltage between this point and the ground, where V is equal to 0, is equal to 10 volt. So basically, this node is equal to what? This node is equal to 10 volt. So now I will have node 1 and I will have node 2. I will not apply KCL to this node. Why? Because I already know the voltage. So I will say here KCL at node number 1. So again, this is a current that enters the node. Do not touch it. Leave it as it is. This current, I will assume it leaving the node, and this current also leaving the node. So, okay, let's see the equation now. Now we will solve this question fully. So the current that goes to the right is V1 minus 10 divided by 2 plus the current that goes up, V1 minus V2 divided by 5. And this current enter the node, so minus 1 equal to 0 or equal to 1. Either way, minus 1 equal to 0 or it's equal to 1. Okay, so now let's make the equation look nicer. So let me multiply by 10. So if you do that, this becomes 5 times V1 minus 10 plus 2 V1 minus V2 equal to 10. Okay, so we have here 5 V1 minus 50 plus 2 V1 minus 2 V2 equal to 10. So 5, 1, 2 V1, so this is 7 V1 minus 2 V2. This take it to the other side, and this is equal to 60. And this is my first equation. It's a nicer form now, and I can use it later on to solve for V1 and V2, which are the ones that we need to find in this question. We need to find V1 and V2 actually. Then we will apply KCL at node number 2. Okay, so we'll assume the currents are leaving regardless of anything I have assumed in the previous step. So we will have here V2 minus 10, V2 minus 10 divided by 10 plus V2 minus 0, the current goes down, divided by 5, plus the current that goes up here, V2 minus V1 divided by 5 equal to 0. Again, I will multiply this times 10. So this becomes V2 minus 10 plus 2 V2 plus 2 V2 minus V1 equal to 0. So we'll have minus 2V1, which is here. Then we have 2V1 and 2V1 and V1. So it's plus, sorry, V2 plus 5V2. And then we'll take 10 to the other side. So this is 10. This is number 2. So now we have two equations. We need to solve them. Then we can represent one in terms of the other, or we can do some simultaneous math. So what if I multiply equation number 1? Equation number 1, I will multiply it times 5. So this becomes 35 V1 minus 10 V2 equal to 300. So this is equation 1 prime. And then equation number 2, I will multiply it times 2. So this becomes minus 4V1 the plus 10V2 equal to 20. And this is my 2 prime. Now, if I add these two equations, add them. So if we add these two equations, add this plus this, it becomes 31 V1. This will cancel. We are multiplying them so that we'll get rid of V2. So I multiply them by a factor so that V2 will be 1 minus, 1 plus. So when we add the two equations together, I get rid of V2. So this is one way to solve the equations. Equal to 320. So from this, your V1 is equal to 10.32. And then come and substitute in this equation or in the other equation, then you will find that your V2 is equal to 6.129 volt. Okay, someone says, okay, I have a different way of doing this. By all means. So for example, what you can do here, let me show you another way of doing this, although this is not a math course, but these basic things are very important to be able to solve. So let me just insert here one slide and show it to you how to do this. This is not from my side. This is from the computer. Sometimes it acts strangely, so that's okay. We used to it. So let me write down the two equations I just had. So this becomes 7V1 minus 2V2 equal to 60. So this is the first equation. The second equation, we have minus 2V1 plus 5V2 is equal to 10. So basically what we can do, we represent one variable in terms of the other. So you can say here that your, for example, in equation 2, minus 2V1 is equal to 10 minus 5V2. So it means that your V1 is equal to 10 divided by minus 2 minus 5 divided by minus 2 V2. So this becomes minus 5 plus 2.5 V2. So this is your V1. So we got that from equation 2. So we'll take this value and we substitute in equation 1. So substitute V1 in equation number 1. So if we substitute, then it becomes 7V1 minus 2 times minus 5 plus 5 over 2 or 2.5. It doesn't matter. Sorry. I did it the other way around. Sorry. Basically, I need to substitute for V1, not for V2. So this becomes 7 times minus 5 plus 2.5 V2. So 7V1, this is your V1 minus 2V2 equal to 60. So we have one equation with only V2, then we will find V2 from this. Once we know V2, we know that V1 is equal to minus 5 to over half V2, then we can find V1. So this is another way. So either you work on the two equations at the same time, or you can solve one variables and then find with respect to the other variable. Okay, well, I can go. Okay, here is the solution. So if you have any question here. So Robert, do you have any question here about this? Okay. So as I said, now this is math, and usually when we do the grading, we give 60% usually on writing the electrical equations correctly. This is 60%. And 40% for the math, how to solve these equations. Now this becomes math, but math is an integral part of the question. So we give good weight for it, around 40%. But of course, writing the right equations is a bit more important because this is an electrical course, that's not a math course. So we need to test you that you understand how to apply KCL, nodal, KVL. That is more important than solving the math. But as I said, nevertheless, the math is also important. And without the math, you will not be able to get good grade in this course. So let me see here. Rahmin, Waqar. So equation is not fixed and depends on the location of course, it's not fixed. There's nothing called fixed. So here it depends on the node, the resistors, we will have different equations. However, what I'd like you to practice, and you're trying to keep this in mind, always assume the currents are leaving. That will make your life much, much easier. Okay? Okay, the last thing I'd like to do here, this equation. This equation, we did it before, if you remember, but we did not solve it actually. We just assign currents. Now, when you look to this circuit, we have VA, VB. Now, this is my ground, V equal to 0, here V equal to 0. And this voltage, V is equal to 13. So we have 1, 2, 3, 4 nodes. This is equal to 0. This is equal to 13. So I end up only having 2 nodes, and that's it. 2 nodes means what? I need only 2 equations. Once I know VA and VB, I can find anything in the circuit. So let's do this. Let's apply KCL at VA. So if I apply KCL at VA, assume all currents are leaving. So the current that goes up here, it is VA minus 13 divided by 1. Why 13? Because 13, because this is the voltage here. Current to the right, current to the bottom. Current to the right is equal to plus VA minus VB divided by 1 also, plus VA minus 0 divided by 1 equal to 0. So from this, we have 3VA minus VB equal to 13. So this is my first equation. Then KCL at VB. Again, assume all the currents are leaving. So here we have VB minus 13 over 1, the current that goes up, minus 13, plus VB minus VA divided by 1, plus the current that goes down, VB minus 0 divided by 2, is equal to 0. Now, if we add terms here, let's multiply by 2 to get rid of this 2. So this becomes 2 VB minus 13 plus 2 of VB minus VA plus VB equal to 0. So let me add terms. So we'll have minus 2VA plus 2VB and VB, 5VB, and this is equal to 26, and this is your second equation. So you have 2 equations. Okay, so if I take this equation, equation 1, and multiply it by 5 to get rid of 5VB. So multiply by 5. So this becomes 15VA, okay, minus 5VB equal to 65. And this is your 1 prime. Now, if I add these 2 equations together, so this becomes, so we add these 2 equations. So we have 13VA. This will cancel, and this is equal to 91. And from this, your VA will equal to 91 divided by 13, which is 7 volt. Now, if I know VA, I can substitute in any equation, 1 or 2. Your VB basically is 3VA minus 13. So your VB is equal to 3VA minus 13. And if you substitute here, this becomes equal to 8 volt. So what is the current? IAB equal to VA, which is 7. Now, why I said VA? Because this is the current direction given in the question. So VA 7 minus 8 divided by R, which is 1, which is minus 1 amp. And this is the same value we have from the previous question. So I ended with this example to show you the justification. Instead of working with 6 equations, I can work only with 2 equations, which is much, much less than the other technique, and this makes our life much easier. And by the way, nodal analysis is the one of the best techniques in circuit, and even some of the packages, the simulation packages, they are based on nodal analysis because it's a very very efficient technique for the circuit analysis. Of course, it works in any circuit. Nodal analysis, and as I said, we will see later on, you will see myself that I'm only using nodal from the final. I mean, for the final, in the final, I will not ask you to use any specific technique. I will leave it for you. But you will notice that most of the time, unless if the circuit is just one loop, that nodal doesn't make any sense. I will always use nodal in solving the circuits. So here, I think let me stop the recording.